If you've ever looked into a pool of water, you'll notice that things inside the water look like they may be in one location, but if you reach down to try to grab them, they're not quite where you expected them to. They'll be close, but they won't quite be where you thought they would be. And what's going on there is a process called refraction. It is the process of light traveling through air, and then it meets the water and bends off in a different direction. And that bending of the light into a new direction throws off our perception of where objects are located. Because what our eye thinks is that light is going to go straight like this. That's what our eye expects, what our brain expects, but it doesn't do that. And the bending of the light causes objects to appear in the wrong locations. And that's why things look kind of wibbly wobbly if you're outside of water looking in. But if you actually get under the water and now you're looking around underwater, it's not so bad. It's easier to reach out and grab things because there's no refraction. When you're entirely within a medium, like water, light goes straight. It's only at the surface where you have this bending action. So we're going to talk about Snell's law. This is the law that describes how light bends as it passes from one medium to another. Snell was a guy about 400 years ago. It's pretty recent, mathematically speaking. And what he came up with here was really a billion-dollar equation. If he had only known that this was going to lead to the telecommunication industry becoming a multi-billion-dollar communications channel. And the way it does it is by passing light, like I have here, down tubes, which are not tubes of water, they're tubes of glass. But what makes the telecommunication industry work, what makes fiber optic cables work, is they have found a way so that light's coming along where they trap it. They trap it so it just bounces back and forth in this tube, and it cannot leave the tube. And the way they trap it is by using this law of refraction that Snell discovered. You'll notice in this diagram up here, I have three scenarios drawn. One is the situation I described with you looking into water and the light getting a little bent. Two is if this angle becomes a little different in such a way that when it's bent, it gets bent exactly along the surface of the water. That's called the critical angle, where the light can't get out of the water, but it's so close to getting out. And then once you go past the critical angle, well, now it's not even close to getting out. Now it just bounces back and forth within it. What we want for telecommunications is this situation all the way on the right, because that way you can keep light inside a fiber optic cable and transmit it down this long cable and get information out the other side. That's useful. When light squeaks out the side of the cable, kind of leaking like I have in this situation here, that's not useful. That means you're losing the information that you're trying to transmit. So critical angle is a very, very important concept for the telecommunication industry. And based on how you design your cable, you will have a different critical angle within that cable. So what we're going to do here is calculate the critical angle for a certain cable. I'm telling you that the core right here has an optical density of 2.22. Okay? In other words, the index of refraction. So let me draw what we're getting at here. Inside this cable, n equals 2.22. Outside the cable, where you have air, n equals 1.00. And I want to know what's the critical angle. Well, let's go back to this diagram, back to our definitions. The question I want to know is, what is theta 2 if theta 1, right here, if theta 1 equals theta c, the critical angle? So once theta 1 equals theta c, what does theta 2 equal? Well, look at the picture in the middle. Where's theta 2? Where did it go? It's still there. It's just that angle right here. So that is 90 degrees. So when theta 1 equals theta c, that's this critical angle that's so important to us, theta 2 equals 90 degrees. Well, plug that into Snell's law, and let's see what we get. N1 times sine of theta 1, but this is now theta c, right? We're at the critical angle. That equals n2 times the sine of 90 degrees. Okay. Now, that just means n1 times sine of theta c equals n2. You remember that sine of 90 degrees is just 1. And I can rearrange this further to say sine of theta c equals n2 divided by n1. And that means theta c equals, I'm running out of room here. Hold on, let's bring this down here. This is the big important thing. Theta c equals the inverse sine of n2 divided by n1. Okay, where n2 is the optical density of the fiber, and n1 is where n2 is the optical density of air, and n1 is the optical density of the fiber. Okay. Now, if you got them mixed up, you would know really soon, because when you try to do that arctangent or that arc sine, it'll break. It'll say, "Oh, that's not possible." So here's what we're putting in here: the inverse sine of n core, that's n1, 2.22 divided by and 1.00 on the top. Okay, so that'll tell us what our critical angle is for this particular fiber optic core. And here's what I mean when I said it would break. If we got those n's mixed up like I almost did right there, and you did 2.2 divided by 1, and you tried to take the inverse sine of that, it's going to be a domain error. You can't take the inverse sine of something bigger than 1. So you can only take the inverse sine of something that's less than 1. The absolute value of it's less than 1. So we plug this into a calculator, and let's see what we get. I'm going to do the inverse sine of 1 divided by 2.22. And what I get, I'm in degrees. I think that's a useful way to operate for stuff like this. Theta c, the critical angle, equals 26.77 degrees. That's the answer to this particular problem. Now, in terms of what that means, here's what it means. It means if you have light that is coming along at, let's see, at some angle of about 26.7 degrees, that light will be bent so that it stays entirely within the optical cable. But if it comes along at a different angle, maybe one that's steeper and pointed more towards the edge, well, that's going to pop out the side. That will not stay within the cable. So the higher this value right here, as this number gets bigger and bigger, you'll see that more light stays within the fiber optic cable. That's why it actually pays really good money to find big values of N. If you can find a material that has a higher value of N, that means you just invented a fiber optic cable that keeps more light inside it, and that's big bucks.